So in Tuesday's lecture, I was talking a bit about residuals, and I got to on the screen in a minute where I got to in Tuesday's lecture. But just to remind you, the residuals are defined to be the differences between the observed data values and the fitted values. And we can write that in vector form, so remember that y is the vector of the observed values, and x beta hat here gives you the vector of the fitted values. So beta hat here is our estimated parameters which we fit using the least squares method. So we've already seen how we fit those. Okay, so this gives us the vector of the residuals. We also have, when we went through the notes on Tuesday, that theorem 1 tells us that the estimated vector of the coefficients, the beta hat, this can actually be written in terms of the design matrix x and the observed values y. So you make this matrix x transpose x to the minus 1 times x transpose. If you then multiply that matrix multiplication by the data value vector y, that gives you your beta hat, your vector of the estimated parameters. I should have on the right to make it a vector. So, because we've got y here and x beta hat here, and beta hat can be expressed in terms of y, that means we can actually write E in a different way, which is a matrix times y. And that matrix, we have the identity, the n-dimensional identity matrix here. So identity times y will give us the y. And then we have this term, this x times x transpose x to the minus 1. X transpose x to the whole x transpose x bit gets to the minus 1, then times x transpose. So this matrix, if we multiply it by the vector y, will give us the vector of the residuals. And towards the end of Tuesday's lecture, we gave this matrix here a name, we called it M. And M has some useful properties. In particular, M times the design matrix x is 0, and M is an idempotent matrix, which means that M squared is actually equal to M. And task 2 in the notes is where you can check that M squared is genuinely equal to M and Mx equals 0. Okay, so where I finished Tuesday's lecture, we've got the because we're now writing the residual vector E as my, we can think of the variance-covariance matrix of this residual vector E. We can use the standard theory on linear transformations to say that that variance matrix of E is M times the variance matrix of Y times M transpose. And then we went through that to say that in fact that means it's sigma squared M, and here we use the fact that M is idempotent, M squared is equal to M. Okay, so that means that if we're interested in the variance matrix of the residuals, that is M times sigma squared. So we can think of it in terms of that M, and that's what I'm now going to be talking about. Okay, so first of all, I'm going to make a statement about linear algebra. So we've seen that M is an idempotent matrix. M squared is equal to M. M is not, at least it's not normally, might be very special cases where it is, the identity matrix. So M is not the identity matrix, and it's idempotent. Now, for a matrix that is not the identity matrix to be idempotent is a rather special property. And there are two things which are consequences of that. One of them is that it's not an invertible matrix. So it's a singular matrix, it's determinantly 0. It's not It's not invertible. And the other thing is that its rank. Now remember that the rank of a matrix you can think of as the number of linearly independent rows of the matrix, or indeed the number of linearly independent columns of the matrix, they're the same. That's the rank of a matrix. The trace of a matrix is the sum of the elements going down the diagonal of the matrix. Now it's a theorem that if you have an idempotent matrix, the rank and the trace are the same number. Okay, so that is a theorem of linear algebra. It's stated in the appendix, which I mentioned on Tuesday, which you can find on the MOL pages. So I'm not going to prove this fact, because it's clearly a theorem of linear algebra, something we're going to use in the statistics. It's going to turn out to be quite useful to us in seeing how we're going to estimate, in particular, the underlying variance in our linear model, sigma squared. Okay, so the rank and the trace of an idempotent matrix are the same. So let's work out one of them. Let's work out the trace of this matrix M. Okay, so M was defined as this matrix here. Identity minus x times the inverse of x transpose x times x transpose. Okay, so we're going to try and work out the trace of this. Now, the trace of the identity matrix, n-dimensional identity matrix, is just n, because it's got ones all down its diagonal, there are n of them, so the trace is definitely going to be n. If you subtract one matrix from another, as we're doing here, then you're simply going to subtract the traces, because that's what you're doing with the diagonal elements. So you must get that the trace of the identity, the trace of M, with the trace of the identity minus the trace of this other bit on the end. So let's do that. So the trace of the identity bit is N. Now the trace of the bit on the end, we're going to use one more property of the trace of a matrix, which is that the trace of a product doesn't depend on which order you take the matrices in the product. So you'll recall that matrix multiplication is not commutative, so AB is not the same as BA usually, but the trace is the same. The trace of a matrix product AB is the same as the trace of the matrix product BA. So that means that we can reorder the terms in that second bit, that complicated bit involving the x's. So we can write it instead as the trace of x transpose x to the minus 1 times x transpose times x. So that's just a reordering of the three matrices that we're multiplying together in that bit on the end. Now, x transpose x inverse times x transpose x is, of course, the identity matrix. However, it's not the n-dimensional identity matrix because of the order that we've got this and the shape here of x transpose x. So x transpose x is actually a p by p matrix. So we're actually getting the trace of the p-dimensional identity matrix, which is p. So we've got the trace of the n-dimensional identity matrix minus the trace of the p-dimensional identity matrix. So the trace of n turns out to be n minus p. Okay? Now, that allows us to conclude that the rank of m, the number of linearly independent rows of m, that is also equal to p. Okay, so now we're going to use what the trace is, because it's n minus p, to see how we can estimate the underlying variance, sigma squared, in our model. Okay? So, the covariance matrix, okay, covariance matrix of the residual vector E, we saw that was sigma squared times this matrix M that we've been talking about. Now, so that means that the diagonal elements of M are the variances of the components of this vector. So they're the variances of the individual residuals. Now, we also saw on Tuesday that the means of the individual residuals are 0. And we also saw that by applying the linear transformation theory to this way of thinking about E as m times y. Okay? Now, if a random variable has mean 0, then its variance is the same thing as the expected value of its square. Okay? And that's because of the way we define variance. So the mean is 0, the variance is simply the expectation of the square of the random variable. So we can actually say that those diagonal elements of sigma squared m are the expected values of the squares of the residuals. Okay? Now, because we know that the variance matrix of E is sigma squared times m, that means that we know that the variances, which are the expected squares of the residuals, are sigma squared times the diagonal elements of m. So the expected value of the square of the ith residual is sigma squared times mii, ith diagonal element of m. Okay? So, what happens if we think about the expectation of the sum of the squares of the residuals? Okay, which remember was the statistic that we tried to minimise when we did the least squares estimation. So the expectation of a sum is the sum of the expectations. That applies to any random variables. So it's actually the same thing as the sum of the expectations of the squares of the residuals. And we've just seen what the expectations of the squares of the residuals are. They're sigma squared times the ith diagonal element of m. So this sum of the squares of the expected values of the squares of the residuals is going to give us sigma squared times the sum of the diagonal elements of m. So the expected value of the sum of the squares of the residuals is sigma squared times the sum of the diagonal elements of m here. Now, of course, the sum of the diagonal elements of m is the same thing as the trace of m. That is, the definition of the trace of a matrix is the sum of the diagonal elements. So, that sum of mii if y equals 1 to n, we know what that is. It's the trace of m, which is, by the calculations on the previous slide, n minus p. So, the expected sum of the squares of the residuals is equal to sigma squared times n minus p. So, let's say that what we want to do is to estimate sigma squared, which, remember, is an unknown parameter of the model. Okay, it's the variance of the random term in our model. So, we can see that the expected value of the sum of the squares of the residuals is equal to sigma squared times n minus p. So, if we want an unbiased estimator of sigma squared, we can see that if we divide this sum of the squares of the residuals by n minus p, the expected value of that statistic, sum of the squares of the residuals divided by n minus p, is going to be sigma squared. And so that means that that is going to give us an unbiased estimator of sigma squared. So let's see that now on the next slide. So that suggested that taking the sum of the squares of the residuals in the fitted model and dividing by n minus p gives us something whose expectation is sigma squared times n minus p divided by n minus p, which is sigma squared. Okay? So we'll call the sum of the squares of the residuals SR. So you can see that that sum of the squares of the residuals has become SR on the right-hand side. Then this sigma hat squared is an unbiased estimator for sigma squared. Okay, so remember the unbiased estimator is one whose mean is the thing that it is trying to estimate. Okay, and one of the things that people often want from an estimator is that they are unbiased. In itself, being unbiased doesn't mean that it's a good estimator. In some settings, it's possible to come up with very bad estimators which are nevertheless unbiased, but in this setting, this is actually the standard estimator for sigma squared. So the standard estimator for sigma squared is this sum of the squares of the residuals divided by n minus p. Okay. A bit of distribution theory, which I'm not going to go into great detail on, tells us that if we look at the multivariate normal distribution with the covariance matrix which was given by this M, and we take the sum of the squares of the components of such a multivariate normal distribution, we get a chi-squared distribution with n minus p degrees of freedom. And the reason why it has n minus p degrees of freedom is because the rank of that covariance matrix, M, is equal to n minus p. So the sum divided by the sigma squared, the variance, so note that is the true variance, not the estimate sigma squared at, has a chi-squared distribution with that number of degrees of freedom. Okay. So that's going to be useful to us when it comes to thinking about the distribution theory later on, and particularly when it comes to constructing tests. So the sum of the squares of the residuals divided by sigma squared has a chi-squared distribution with n minus p degrees of freedom. Okay, let's look a little bit more R output. So, in Tuesday's lecture, I introduced this data set of tractors with their ages and maintenance costs, and we fitted a linear model to that data set. So some of the output looked like this. This is just a small part of it. And one of the things it gave us was the residual standard error. And you'll see that it says it's 283.5. Okay, so now I'm going to tell you what the residual standard error means. The residual standard error in that R output is sigma hat. So, a couple of slides back, I defined the square of sigma hat. Obviously, sigma hat itself is the square root of that. So it's the square root of the sum of the squares of the residuals divided by n minus p. So that is the residual standard error which appears in R. So the output, the R output showed it was 283.5. You can calculate it directly in R and confirm that the formula that we've given gives you 283.5 or something that rounds to it. So what's going on here? So tractor.linear.lm was the R output that we created, which contained the outcome of fitting the linear model to that data set. $resid gives you the residuals from that linear model. So remember that I said on Tuesday that if you happen to put a dollar sign after an R object, you can then extract various things from that object, and $resid on a linear model object extracts the residuals from the object. the squaring here gives us the squares of the residuals, and then we're going to sum them. Divide by 15, take the square root. So that calculation will give you the calculation that R does to get the residual standard error. Okay, and you can see that the answer does indeed match. Okay, so remember I said the degrees of freedom, there are 17 data points in this data set. We're fitting a simple linear regression model, so P is 2, because there are 2 parameters that we estimate, so there are 15 degrees of freedom. Something that you might want to do, so I'm now just over halfway down page 13 in the lecture notes, is to find the variance matrix of the beta hats, the estimates themselves of the parameters. And R has a function which does this called vcov. Okay, so if you enter again with the tractor data, vcov of the linear model that we created for the tractor data, tractor.linear.lm, then this is the output we get. So it's a matrix. The beta hat has 2 components, the estimate of the intercept and the estimate of the gradient, so the coefficient of age. And we see here the variance and covariance matrix, so the diagonal elements are the variances of the estimators, and the off-diagonal elements are their covariances. Okay, so we can interpret that output. So, for example, the estimated variance of the estimate of the intercept is that top left number. And if we take the square root, we will get the estimated standard error of the estimate of the intercept. Okay? And if you look back to where we have the summary output, you will see, so in the notes, this is back on page 11, you'll see the intercept under the standard error column, you get 146.94, and that is the square root of the estimate that I've just shown you from the matrix. You can also read off the estimated standard error of the estimate of the gradient, coefficient of age, so that's the square root of the other diagonal term, and there you get 35.61. That also matches the entry in the table halfway down page 11. So we also get the off-diagonal entry, which is the estimate of the covariance between the estimate of the intercept and the estimate of the gradient. And that turns out to be about minus 4,000. Remember that we can calculate the correlation. The correlation is the covariance divided by the product of the 2 standard errors. And that turns out to be, it's minus 0.8837. So you can do that calculation using the numbers in the matrix on the previous slide. So that means that there's quite a striking negative correlation between the estimate of the gradient and the estimate of the intercept. And I will very briefly try to explain why you might expect that to be the case. So here's a cloud of some data. So we're going to fit a line through it. Something like that. So the intercept's down here, that's the gradient. To imagine if our data looked a little bit different, and instead slightly different coloured chalk. So let's say that instead we ended up with an intercept which was a bit higher up. Then that's the bottom of the phone by mistake. So if the intercept ended up a bit higher up, then when the data tends to be in the same sort of area, we're going to get a lower gradient, because you're getting a flatter looking line to get to this area where the data points are than if we had the intercept down here. So it makes sense that a larger intercept tends to correspond to a lower gradient. Okay, certainly in an example like this. Okay, we actually calculate the matrix M in R using R's capability for linear algebra, and the code looks a little bit like this. Again, I will put this code on Mole, possibly on Monday, because obviously it's a bit late after the lecture today. So you'll see here that several times we've got the sequence of characters %, %. That is how R does matrix multiplication. So if you want to do the standard matrix multiplication in R, you don't just put a star, you put %, %. So that's from how R has matrix multiplication. So that definition there, so we've defined X using the function cbind, which just gives us a row of ones and the ages, and then the M's here, so M here, we've defined in exactly the form that's here, but with this %, % to indicate matrix multiplication. Okay, the 17 is because there are 17 data points. Solve, we've got solve of the transpose of X times X, matrix multiplication. Solve gives the inverse of the matrix, so it corresponds this X transpose X to the -1. So again, the little t of X gives you the transpose of X. So that's just a little bit of R linear algebra. Solve to find the inverse, t to find the transpose, %, % is matrix multiplication. Okay, so we can actually look at M and see what we get. I've said in the notes that it may not be that easy to read. It's a 17 by 17 matrix, and the way the 17 by 17 matrix is displayed may not be that easy to read, but we can see what it looks like. The diagonal terms, which remember that are the variance of the residuals divided by sigma squared, in this case range from 0.785 to 0.939, so they're a little bit less than 1. The off-diagonal terms are related to the covariances, and hence to the correlations of the residuals, and they're quite small, but they're not 0, and they're mostly negative. So typically, one residual is slightly negatively correlated with another residual. And that's actually not that different an idea from what I was doing over here. If you're tending to get, if your estimated line is going a little bit high in one area, then that often means it's going a little bit low in another area compared with your observed data. Okay, so a bit more about the distributions of the estimators and the residuals. Okay, so remember that we assumed that the random part of our model, so the epsilon ends, the epsilon term, sorry, has a normal distribution, multivariate normal distribution, mean 0, and the covariance matrix should just be sigma squared times the n-dimensional identity matrix. So that means that they all have so this is the random terms, they all have mean 0 and variance 1, sigma squared, sorry, and they're independent of each other. Okay, now, linear transformations preserve normality. So that means that our y, which is x times beta plus epsilon, that's a linear transformation, so that's also going to end up with a normal distribution. And it's now, again, an n-dimensional multivariate normal distribution, with, now the mean vectors are the x betas, this is with the underlying betas in the model, so the coefficients, and the same sigma squared times the identity. Okay, now beta hat and the estimates of the parameters and E, the residuals, are both linear functions of y. So beta hat is defined by that one, and E is defined by that one. So they're both linear functions of y. Normality is preserved by linear functions, so they also have multivariate normal distributions. And we can work out what the distributions are. Now, in fact, we already know the means and variances, so really the extra input here is that the distributions are normal. So beta hat has a normal distribution, p-dimensional, its mean is beta, and that's its variance. The residuals, E, also have a multivariate normal distribution. Their mean is 0, and their variance is sigma squared times n. So as I say, the extra content here from what we've already seen is that normality is preserved. So these distributions are indeed normal. Now, extra properties that come from being multivariate normal. One is that beta hat and E, so the estimates of the parameter values and the residuals, these are actually independent random variables. Now that may seem a little bit surprising because of the way they interact with each other, but that is thinking of them. Given a particular set of beta values, our estimates of beta hat and the residuals are independent. Now we can prove that using the linear transformation property again. And we do it using a matrix, so this may look like a vector, but this is actually a matrix. On top here, we've got the matrix x transpose x to the minus 1 times x transpose, which appeared here. And on the bottom we've got m, which appeared here. So if we do that, we're going to get a longer vector, beta hat E, as equal to a times y. Okay, so the top bit will come from the x transpose x to the minus 1 times x transpose, and that will give us beta hat. The bottom bit comes from the m, multiplied by the y, gives us e. So we can write beta hat e, this is a longer vector which contains both the parameter estimates and the residuals, as a times y. So now, if we want the variance of this vector, underline them for you, indicating vectors. So if we want the variance of this vector beta hat E, variance matrix, by our usual property of linear transformations, this is A times the variance of y times A transpose. Now the variance of y we know is sigma squared times the identity matrix. So this is actually sigma squared times A transpose. So that's again the identity matrix cancelling down. Now, we can do ordinary matrix multiplication style things with matrices written like this, with one matrix on the top and another matrix on the bottom. We can apply our usual matrix multiplication rules. So, top left, we're going to get x transpose x to the minus 1 times x transpose squared. That bit's not going to matter very much, in fact. Then here, we're going to get, got that wrong, we don't want to square it because we're actually going to take the transpose of it in the second term. Fortunately, as I say, it doesn't really matter very much because it's going to be a bit of a mess. want x transpose x to the minus 1 times x transpose, all transpose the second term. Then, top right, x transpose x to the minus 1 times x transpose. We're taking the transpose with the second one, so we get m transpose. But in fact, M is a symmetric matrix, so that is going to be M. And then down here, we get M times the transpose of the thing on the top. And the transpose of the thing on the top, we get the x first, and then x transpose x to the minus 1. And down here we get M times M transpose. So that's what we get if we do A times A transpose. Now, the good news is that the mess here doesn't matter because we showed that mx is 0. So mx here is 0. Covariance matrices are symmetric, and x transpose m transpose up there is therefore just the transpose of mx. It's also going to be 0. So we actually get sigma squared times, I'll just write mess rather than writing it out in full, m squared down here, but the key things are the zeros here and here. So the covariance matrix of this beta hat E is something which has zeros in these areas. So remember, these are actually big matrices, so these are big arrays of zeros. So that tells us that the covariance between the beta hat terms and the E terms, those covariances are all 0. Okay? Because these have multivariate normal distributions, again, normality is preserved by linear transformation, that tells us that they're actually independent. If coefficients, so if components of multivariate normal distributions have covariance 0, they are in fact independent. Okay, so that shows us that beta hat and E are independent random variables. Okay, so I'm going to move on to another set of slides now. And in the rest of today's lecture, I'm going to talk a little bit about maximum likelihood estimation for linear models. Okay, so we have unknown parameters given by the beta variables, so the coefficients in the model, betas, and sigma squared is also an unknown parameter, the variance of the random term. Okay, so we can write down the likelihood because we know that our data has a multivariate normal distribution, as we just described. Y has a multivariate normal distribution under our linear model. Okay, so we can apply the multivariate normal density, and we get something which looks like this. I'm not going to read it out because it's a multivariate normal density, it will take quite a long time. So this is from the form of the multivariate normal distribution, and we've used the fact. So then this becomes essentially, when we work with likelihoods, we don't mind the fact we're not interested in constants which don't depend on the things we're trying to estimate. So the things we're trying to estimate are sigma squared and beta. Those are our unknown parameters. So where things don't depend on sigma squared and beta, we've taken them out as a constant, and we've just written proportionality term here. So the likelihood is proportional to this expression, sigma to the minus n times the exponential term. And note that this looks very much like the definition of the residual sum of squares. And that's what this is, the residual sum of squares. Okay, so in this fact, we've used the fact that the determinant of sigma squared times the identity matrix in n dimensions is sigma squared to the n. And the reason why we need that is because in the form of the normal density, you have the determinant of the covariance matrix appearing in that form. Okay? And so we need this fact to obtain the sigma to the minus n that appears at the front. Okay, so maximum likelihood estimation, we want to maximise this likelihood. Now, as you probably remember, if you've done much likelihood-based statistics before, it's usually easier not to try to maximise the likelihood itself, but to maximise the log likelihood. So we take the logarithm of that likelihood, and it's minus n times log sigma, minus 1 over 2 sigma squared, times the residual sum of squares, if that is the true values of beta, plus a constant term which I've written as c. Now the c term there does not depend on beta, and it does not depend on sigma squared, and that means that when we're maximising the log likelihood, we can ignore it. I mean, we'll be differentiating, it doesn't depend on beta or sigma squared, so we can just ignore it, because it's going to be 0, give 0 when we differentiate. So we can ignore that term when maximising. Okay, so what do we need to do? We need to minimise the sum of squares. Okay, we look back at our log likelihood. We want to maximise this term, so we've got a bit involving sigma at the front, and then we've got this sum of squares bit involving beta. So to get the optimal beta, we simply need to make that term as small as possible. We're maximising the likelihood, there's a minus sign there, so maximising the likelihood is going to involve minimising this sum of squares term. So it turns out that because we've assumed that our random variables have normal distributions, maximum likelihood estimation comes down to the same thing as least squares estimation as far as the beta terms are concerned. Okay, so we're exactly now trying to minimise the residual sum of squares. And that's what we need to do to maximise the likelihood. So that tells us that we don't need to do any more work to find the maximum likelihood estimates of the betas. We've already done it. They're the least squares estimators that we've already found. Okay, so maximum likelihood estimation gives the same estimates for the betas that we already know about. Okay. So the next thing we might want to do is to find the maximum likelihood estimates of sigma squared. Okay, we've already got the log likelihood, previous slide. So once we've found our maximum likelihood estimates of beta, we can put in the value of the likelihood we get in that case, and we can differentiate again, now with respect to sigma squared, and then we'll get a maximum likelihood estimate for sigma squared. Okay, so that's what we get. We can now substitute in our actual values beta hat. So these are our estimates of the parameter values. We can substitute those into the likelihood. So now, because we've done the beta part, we're only now thinking of this as being a function of sigma squared. So we can differentiate it to obtain a maximum likelihood estimate for sigma squared. Okay? So we can do this by differentiating with respect to sigma squared. Okay, so task 3 in the note, so this is on page 15, says to verify the form that we get for the maximum likelihood. So you can do this yourselves. One thing I want to warn you about is that it's easy when differentiating with respect to sigma squared to confuse yourself by thinking, say, that the derivative of sigma squared is 2 sigma. Okay? It's not. If you're differentiating with respect to sigma squared, the derivative of sigma squared is 1. So, what I would suggest that you do is replace the sigma squared, before you differentiate it, replace sigma squared with something else. V, say, variance. That then, of course, means you have to replace the sigma that appears near the front with the square root of V. If you do it that way, then you shouldn't get yourself confused when doing the differentiation. Okay? So the answer you get is actually the residual sum of squares, SR, with our estimated parameter values in, divided by n. So the maximum likelihood estimate of sigma, so sigma hat squared, is the residual sum of squares divided by n. Now, we had another estimate of that earlier in the lecture. And that estimate was SR, the residual sum of squares, divided by n minus p, the number of degrees of freedom. And we saw that that was unbiased estimator. So this estimator, SR over n, instead of n minus p, that is not an unbiased estimator. Okay? So that estimator we've just found as a maximum likelihood estimator is a biased estimator. Okay, we divided by n, whereas an unbiased estimator would divide by n minus p. So it's typically going to give an estimate for the variance which is a bit too small, because we're divided by something which is too big, n rather than n minus p. Okay, so as we already discussed, in fact earlier in today's lecture, the